Okay, so in our previous lectures, we talked about functionals with multiple dependent variables. In this lecture, I want to talk about functionals with multiple independent variables. So think we're going to have one function u, but instead of just being a function of x, it's going to be a function of, let's say, x and y, or x, y, and z. Okay, so what we want to do is we want to consider extremizing the functional given by, so we'll say I of u, so just one function, the functional is only a function of a single function, is going to be, we'll use two dimensions, x and y, so we'll say integral over the area here of some function f, which will now be a function of x and y, and it'll also be a function of u, and I'll put that, remind you here that this is a function of x and y. And then now we need to, instead of just talking about u prime, we need to talk about partial derivatives, so we'll say u partial with respect to x, which will also be a function of x and y, u partial with respect to y, which will be a function of x and y. So that's the equivalent of that first class of functionals that we've looked at, and we'll say this is dx dy. We'll call this equation 1. I'll just remind you too that just from a notational perspective, so where the quantity ux, as I write it here, is going to be equal to partial of u with respect to x, and the quantity uy is going to be equal to partial of u with respect to y. So we already know how to extremize a functional. We're going to take the first variation and set it equal to 0 to get the following. So we'll say delta I, the variation of I, is equal to 0. And what is that variation? Well, here's our integral over the area. Partial f with respect to u, delta u, plus, so just like we couldn't have a variation on x, we can't have a variation on x or y, so that's why we start out with partial f with respect to u. And then partial f with respect to u, partial with respect to x, times delta u of x, plus partial f with respect to u y, remember this is partial with respect to y, times delta uy, right? So that is our first variation, dx dy, call that equation 2. Okay, so what did we do in the past? Well, in the past, we took, let's say, this derivative term and we integrated it by parts. So in the case of multiple independent variables, we don't integrate by parts. The corresponding procedure to integration by parts in 2 or up to n dimensions is the divergence theorem, right? So we'll use that in a minute, but I just want to observe the following. What I want to do is just consider this following quantity, d by dx of the quantity partial f with respect to ux delta u. What is that derivative? Well, that looks like d by dx of partial f with respect to ux times delta u plus, this is just a product rule, right? Plus partial of f with respect to ux times d by dx of delta u, right? That's just the product rule. Okay, let's go ahead, we'll bring this down. This is d by dx partial f with respect to ux delta u plus, now what is this quantity? Well, we already showed in actually our initial lecture on variational methods, or rather when we talked about the delta operator, that the derivative of the variation is the same as the variation of the derivative, so that we can write this is equal to partial f with respect to ux. Now this is just delta ux. Okay, we'll call that equation 3. Okay, I'm going to rearrange this a little bit. If I rearrange it, you can see up here I have this partial f with respect to ux times delta ux. So I'm going to just bring that out, and so I can make my substitution and say that partial f with respect to ux delta ux is equal to this quantity d by dx of partial f with respect to ux delta u, right, minus d by dx partial f with respect to ux times delta u. Right? Let's call that equation 4. Okay, I could do the same thing except replace y wherever I see an x. And I can just say, so I'll say similarly we could write that partial f with respect to uy, delta uy, is equal to, now d by dy, partial f with respect to uy, delta u, minus d by dy, partial f with respect to uy times delta u. Call that equation 5. So what we want to do now is substitute equations 4 and 5 into equation 2. When we do that, we have that the integral over the area of the quantity, this first quantity is unchanged, so this is partial f with respect to u times delta u, right? Plus, and I'm going to substitute this equation 4 in here, d by dx of partial f with respect to ux delta u minus d by dx partial f with respect to ux times delta u, and then plus d by dy partial f with respect to uy times delta u minus d by dy partial f with respect to uy times delta u. Okay, that whole quantity integrated dx dy is equal to 0. We're going to call this equation 6. Okay, I want to make a little comment on what this d by dx of, let's say, this first term looks like. So this is kind of an aside. I'll just mention that d by dx and d by dy represent total derivatives. So for example, we could write that d by dx of, let's say, this first term, partial f with respect to u of x, right? That equals del squared f del x del u x plus del squared f del u del x times u of x plus del squared f del ux squared times uxx, right? Plus del squared f del uy del ux uxy, right? Let's call that equation 7. So just as an aside, that's what that looks like. Okay? So let's go ahead and now return to the problem of interest, and we'll rearrange equation 6 a little bit. And so that's going to, we'll have this integral over the area, and I'm going to group the terms that have this delta u that I can factor out together. And so I end up with partial f with respect to u minus d by dx, partial f with respect to ux minus d by dy, and then partial f with respect to uy, right? That quantity all times delta u, and then dx dy. So that's the first portion. And then we have another integral that contains these the last two terms that aren't included here. So then we have plus the integral over the area of this quantity here that looks like d by dx of del f del ux delta u, right? Plus d by dy of del f del uy times delta u. Okay, and that quantity integrated over dx dy equals 0. Let's call this equation 8. Okay, so I need to do, you can kind of start seeing that this first integral that I wrote looks a lot like the form of the Euler-Lagrange equation that we had written before, and that this term here is a little bit new. We haven't seen something like this before. So what I want to do is I want to try to rewrite this second integral here in a different form. And in this case, we'll say then this is the integral of a of now this quantity here, d by dx, of partial f with respect to ux, delta u, plus d by dy, of partial f with respect to uy, delta u, okay, dx dy. That's going to be equal to, well, what is this, what could we write this as? Well, this looks like, what if I were to write this first term as d by dx, this is a vector, now d by dy, this is a vector operator, dotted with something that looks like del f, del ux, delta u, and del f, del uy, delta u, okay, and then dx dy. Let's call this equation 9. Okay, what do we know? Well, this is our gradient operator, right? This is del, that vector. And let's just call this vector, for the sake of calling it something, we'll call this vector u. Okay? So what this is del dot u. And now we know, okay, now we can start saying, well, maybe I can use something like the divergence theorem to handle this. And that's exactly what we're going to do. So I want to observe that equation 9 is in the form of the divergence theorem. Right? So let me see if I can remind you here. The divergence theorem said if I have an integral of del dot, in this case we'll call it u, right? Dx dy, that could be written as the integral over the boundary, now we'll call it gamma, of u dot n ds. And what is n? N is the unit normal along the boundary. And let's call this equation 10. So I want to apply equation 10 to equation 9 to get the following. So here we go. I'll write the first side. The integral over a of this quantity now, d by dx, partial f with respect to ux delta u, plus d by dy, partial f with respect to uy, delta u, okay, dx dy. That's going to be equal to this now integral over the boundary of u dot n, right? What is u dot n going to look like? That's going to be, if n is just n1 and n2 in this case, and that looks like partial of f with respect to ux times n1, which I'll remind you is a function of x. It's going to change depending on where we are on the boundary, plus partial of f with respect to uy n2, which is also a function of s. Okay, and then we have a delta u factored out, and then we have a ds. Okay, so what is n1? That's the x component of the unit normal, and n2, of course, is the y component of the unit normal. So let's call this equation 11. And now I'm going to substitute 11 back into equation 8. And I'm left with integral over the area of that initial quantity now, partial f with respect to u, minus d by dx of partial f with respect to ux, minus d by dx, or sorry, d by dy of partial f with respect to uy. Okay, that quantity dx dy. And then I have this boundary integral over the boundary we call gamma of partial f with respect to ux times n1 of s plus partial f with respect to uy times n2 of s, right, times delta u ds, that whole thing equals 0. We'll call that equation 12. Okay, so we're getting very close now. Okay, so what do we have when we look at this? Well, we know that delta U is arbitrary. Oops, and I forgot to write delta U here. Sorry about that, guys. Let's fix that. So this should be delta U dx dy, right? So delta U is arbitrary. So what I can see is that just like we had before, I have a sort of an integral over the domain, then I have an integral over the boundary of that domain. And so in the case where I have a prescribed value of my function on the boundary, then this boundary term vanishes because delta U has to become 0, right? So this delta U goes to 0, this whole thing goes away. Okay, so again, just like we did with all the other cases, we're going to invoke the fundamental lemma of variational calculus, and we're going to arrive at the Euler-Lagrange equations and something about the boundary terms. So when we do that, we get this first integral yields our Euler-Lagrange equation. So number 1, we get the Euler-Lagrange equation. Okay, and that looks like partial of f with respect to u minus d by dx, partial of f with respect to ux minus d by dy, partial of f with respect to uy. Okay, and all of that equals 0. Let's call that equation 13. So that's our Euler-Lagrange equation. How about the boundary conditions? We get the following. We get boundary conditions of the form as follows. Okay, in the first place, we could have that the function u on the boundary defined by s will be specified, right? So if that's the case, then we obviously know this is our essential or geometric boundary conditions. Okay? If u is not specified on the boundary, then this integral term doesn't vanish, but delta u is arbitrary, so we require this quantity in the parentheses to be 0, right? Via, again, the fundamental lemma of variational calculus. So in that case, we have the quantity partial f with respect to ux times n1 s plus partial f with respect to uy times n2 of s. That quantity then must be equal to 0, right? And so this case here, that would be our natural boundary conditions. Okay? We can expand equation 13 if you like and kind of see the full expanded form of the Euler-Lagrange equation. So our expanded Euler-Lagrange equation will look like that first term doesn't change, partial f, partial u, and now we just got to carry out our partial derivatives, right? So this first term becomes partial squared f with respect to x and ux, right? And then we have a y equivalent, so this will be partial squared f with respect to y and uy, right? Okay, now let's continue on. This becomes partial squared f. Let's see, with respect to u and ux, right? And then there's multiplied by ux, and then a corresponding for the y, minus partial squared f with respect to u and uy times uy. Okay, and now we'll continue on through. This becomes partial squared f with respect to ux squared times uxx minus partial squared f with respect to uy squared times uyy. Okay, and then both x and y will yield the same quantity, so those combine, and we end up with a factor of 2 there to say partial squared f with respect to ux and uy, and then that's multiplied times uxy, and that whole thing equals 0. Call this equation 14. So that's the expanded out Euler-Lagrange equation for this case. Okay, I know I just did this for only 2 independent variables, but the procedure could be applied for 3 or more independent variables. It goes on the same. Okay, so we could proceed in a similar manner to develop equivalent functions to develop equivalent equations for functionals with 3 or more independent variables. And so in that case, we've sort of tied a bow around this topic. You now have the tools to develop the necessary extremizing equations that U needs to satisfy for these functionals with multiple independent variables.